Okay. Well, let me welcome everybody here to the third of the SoFiE Seminars. Today, we're very excited to have Professor Neil Shephard from Harvard University as our speaker and Professor Jean-Pierre Florens from the Toulouse School of Economics as the discussant. The format will be the same as in previous weeks. We'll have 40 minutes for the speaker, 10 minutes for the discussant, and 10 minutes for Q&A from the audience. During the seminar, I will be gathering questions, and then from time to time, Neil will take a break to see if there are any questions from the audience. So to ask a question, you can use either the Q&A button, which you should see down at the bottom of your Zoom screen, or you can use the raise your hand feature. And so when there's a gap, I'll collect the questions, and if it's easiest, I'll just ask your question directly myself. Otherwise, I'll call on you, I'll unmute you and ask you to ask your question directly. So now let's start the seminar. Neil, if you'd like to share your screen and we can begin.
Is that working, Andrew?
Yes, that looks great, Neil.
Okay. So I wanted to start by thanking Andrew, Ying, and Noor for doing the organizing of this sequence of seminars. I think it's very important during this difficult period that we come together and keep our community going. And so I want to really thank them for all the work they're doing, and also wanted to send my best wishes to friends of mine who are on this call, and it's a very difficult, challenging time. And so I just want to send my best wishes to you, your friends, and your family. Okay, so this is a joint paper with a rising G4 fourth year PhD student in the economics department, Ashesh, and it's about causality and time series. For those of you who would like control over the slides, I've just added the slides to the SoFiE Seminar Series website, so you can download the slides, and if there's something you prefer to be watching rather than the slide I'm on, then you can do that. So this is the big picture. So in my view, there are three great tasks that statisticians work on, which is description, broadly understanding some variable or big amount of variables y, prediction, which is I see some w, what y's are likely, and causality, which is if I move y around, if I move w around, how will y move? Those are the three big things that statisticians address. Most empirical economics research is about causality. It's about a third of those topics. So you see that in different ways in economics. So for example, there's causality studies for highly structured models, which you often see in industrial organization, for example. There are randomized experimental methods, which you see, for example, in development economics. And then there are observational methods trying to draw out causality, often mimicking experiments. And you see there's basically every area of applied economics, for example, corporate finance. And here we're going to build dynamic causality methods for observational time series. And following the strategy that's used elsewhere in economics, what we're going to do is build a theory for observational causality and observational time series by mimicking what's called a potential outcome time series framework, which has been developed for randomized dynamic experiments. So I'll take the concept that we've already developed for randomized experiments for time series, and we'll try and take that over to observational time series. And this involves developing some new methods. So the new methods, for example, will be a causal response functions. We'll be defining what we mean by shocks, a linear version of a potential outcome time series, and also what we mean by instrumental variables in a potential outcome time series. So we'll build a toolbox for us to learn about causality using observational time series. And many of these topics will be related to classical things which have been developed over the years by time series people and econometricians, such as the impulse response functions, local projection instrumental variables. So in some sense, we're reinventing what's been known for a long time, and other ways it's trying to build a better foundation for thinking about causality and observational time series. I released a paper with Ashesh and Bojinov recently, which extends the ideas that I talk about in this paper to panel data experiments. If people are interested, that's on the archive. Okay. So this is in the context of time series and causality. So we should talk about what we're not doing. So researchers quantify causality in a variety of different ways in the academic literature. The most famous of those is a model-free notion called Granger causality, which is about various conditional independence assumptions being held. And famously, this has nothing to do with causality except for its title. It's about forecasting. But in some sense, it's very, very close in spirit to what we're trying to do, because it's a model-free definition of what it does, but it isn't about causality. And then there are very many model-based understandings of causality. Perhaps in recent years, the most well-known of those are these highly structured models that you see in dynamic stochastic general equilibrium models. There are also game theory versions of these models too. And then there are also state space models with different types of interventions. When I was a student, I studied very carefully Harvey and Durbin's structural time series model, where the intervention was a change in law about seatbelts. So they were trying to understand causal impact of requiring seatbelts on death rates. And then there's equivalent version in the Box-Jenkins world of intervention analysis. And then most famously in economics, as well as the DSGEs, the other bit of famous technology is about linear models, such as the vector moving average, vector autoregressions, and then causality in those contexts, which is impulse response functions, local projection IV. The work that's closest to ours in our view is the brilliant work by Guido Kirsteiner and his co-authors, and there are a lot of relationships with what we do, which we describe in detail in the paper. They're different from what we do, but that's a very important two papers that are relevant. It's a different framework, but they're trying to do relatively similar types of things to us. Okay, these are the main contributions of our paper. So we're going to define a causal response function, which we think is useful for observational studies. And what this will give is a model-free causal meaning to generalized impulse response functions. So if you like a generalized impulse response function, if you know how to estimate that in your context, we'll give you conditions under which you can check whether or not your conclusions are causal or not. And likewise for an impulse response function. So our assumptions will kind of like sit at a meta level above the generalized impulse response function or the impulse response function. And if you can estimate an impulse response function and our conditions are satisfied, then the result will be you can make causal conclusions. So that's probably the most important contribution of the paper. And then we go on and talk about two other things. To relate our work to a lot of work that's done in economics, we also, within the context of potential outcome time series, we define what we mean by shock, what we mean by linearity, and what we mean by instrumental variables. And having defined that, it allows us to understand what a local projection and a local projection instrumental variable estimate is. These are usually studied in the context of vector moving average models, which impose shocks, linearity, and causality all at once. And what our methods allow us to do is to unpack where identification of causality comes from, separating out identification from precision. So precision is how well do I estimate something, and causality, identification is about can I estimate it in the first place. Okay, and what we show in our paper is that shocks help precision, not identification. So in these models, people often talk about we need to find shocks, identify work out shocks in order to identify causal effects in time series models, and we'll just show that that's not actually correct. So that's the main contributions of the paper. So to do this, you need to know what a potential outcome time series is. That was developed in a paper with Bojinov that came out recently in JASA, and it was motivated from a problem in financial economics that I saw in a hedge fund in London. So maybe I'll tell you that story, given it's a financial econometrics talk. So what these people were doing is they had a machine which decided which positions, a quantitative machine that decided what positions they wished to take, and then those positions were executed by trading, and they had a set of human traders and they had a set of computers which traded, and they wanted to know which is better, the human traders or the computer traders. And so in order to do that, they actually randomized orders going to the humans and the computers to allow them to make a causal comparison of the effectiveness of human traders compared to the computer traders. And I thought this was very interesting, and so I had that in mind when I developed this broader, or I developed with Yav, this broader notion of what do we mean by causality in time series. But that's basically in the back of my head. So this is a potential outcome time series. So it starts off with a treatment path. In that case, it would be, do you go to a computer, do you go to a human? So it would be binary, but it's a treatment path, and that's a stochastic process. I'll call that W. Then there are some outcomes, but first of all, there are potential outcomes that we're interested in. That in my context that I was just talking about, these would be the profit or loss from the particular trades that these guys were making, people were making. So the potential outcome path is defined not just for the particular stochastic treatment path that happens, but all possible treatment paths, which I'll write as W1 to T. So the potential outcome path is a stochastic process which would happen if the treatment followed W1T. Okay, so many different W1Ts are possible, but for each of them, we have a stochastic process, and that would be a collection of random variables. Y1 will depend upon that stochastic process. Y2, that's the second trade, will depend upon the stochastic process. Y capital T will depend upon the stochastic process. Okay, so many different possible treatment paths. Each of them will deliver its own stochastic process. Okay, so those are potential outcome paths. Okay, and then we make some assumptions, and the assumptions are very natural for a time series person, but it's good to write them out. So they have three forms. So the first form is we make an assumption for a potential outcome time series that the potential outcomes are not anticipating. That is, at time one for this is profitability on a particular trade, it's only affected by the treatment up to time one. It's not affected by future treatments. Okay, so this is an assumption. W2 is allowed to depend upon the path up to time T2, and then the random variable at time t is allowed to depend upon the entire treatment. So what we've done here is we've got rid of the dependence on the future of the treatment. Okay, so for a potential outcome time series, we need that this holds. Okay, that the outcomes for the y's don't depend upon future treatments. This is a subtle point. I'll illustrate it in a minute, but it's an important assumption. The second one is that what do we see? We see W, we see the treatment path, and we see the outcome path, which is the potential outcomes evaluated at the treatment path. Okay, so that's what we see. So we don't see all of these different potential outcomes. All we see is the potential outcomes at the treatment path that we actually see. And then I'm going to have this notation. FT is a natural filtration generated by the treatment path and the outcome path. And then the last assumption, which is hardest to understand, is what we call non-anticipating treatments. That is, at time t, given the information at time t minus 1, the treatment choice, WT, doesn't depend upon future potential outcomes. The future potential outcomes is independent of the future potential outcomes and a potential outcome at time t. So this looks very constraining. It looks like it kind of rules out forward-looking expectation type models. You'll see that's not the case in a minute. So I'll directly address that. But that's the assumption. The treatment, given the past, is independent of all future potential outcomes and the current potential outcome in here. Okay, so that's the third assumption. If those three assumptions are satisfied, then we say that W and Y are potential outcome time series. So that's the definition that we use for everything. So if those are not satisfied, our paper is voiceless. It has nothing to tell you about in this context. And just to relate this to things that you will have seen elsewhere, assumption 1 is a time series version of non-interference, or some people call that SoFiE in a cross-sectional setting. So non-interference in a drug trial is I take a drug, you take a drug in a drug trial, but your taking of your drug doesn't impact my health outcome. That's what non-interference is. So what treatment you get doesn't impact me. And that's probably true for cancer drugs, and it's not true for vaccines. Okay, so that's like the example. So this is due to David Cox in 1958, and then there's a modern version, SoFiE, but the intellectual version is due to Cox. And then the third assumption is time series unconfoundedness. It says W is independent of the science, which is what the outcomes are in here, all future outcomes. And this really goes back to Fisher. This was Fisher's idea in experimentation, which was choose the treatment randomly from the rest of the science, from what's going on in your fields. And that allows him to do very simple inference in experiments. So this is a kind of classic assumption in the rest of statistics, but this is the time series version of it. And it looks clunky, but it's basically unavoidable in this context. So 1 and 3 have very solid basis on what's going on. So that's basically a potential outcome time series. And that was in my paper with Yav. And what we're going to do is, instead of talking about experiments, we'll talk about observational things here. So that's and in a minute I'll talk about causality. So just to illustrate this, these potential outcomes can be very confusing at first sight, and you can your mind can go a bit crazy on it. And so this picture helps me, which is going to be based on, suppose treatments are binary, then at time 1 there are two possible potential outcomes. You've either been treated or not, And then at time 2, there are 4 potential outcomes. You've been treated first time, then you've been treated second time, or you've been treated and then you've got non-treatment, etc. So you get 4 of them, then you get 8. So you get a doubling each time in a number of potential outcomes. So that's the collection of all potential outcomes. And then if your treatment path follows 1, 1, 0, then your outcome path follows this stochastic process. So it chooses this stochastic process to be observed. And the others are never observed. You never see them as a result of that. So that would be the stochastic process, the observational stochastic process that you see. So that's how all of this links together. It takes a while to kind of get used to it, but once you have it, it feels very natural. But anyway, so this is 2 examples of this structure. So the first is a VAR. So this is a potential outcome version of a VAR. This is the potential outcomes if the treatment path had been W1 to T. It depends upon previous outcomes and the current version of WT. And then it's going to get hit by a shock, and then the W's are linear in here in terms of the past W's, the past Y's. And then here I'm just assuming a simple structure for some innovations, epsilon eta, which are normal and they're correlated. So this is not a potential outcome time series because the epsilons and etas are contemporaneously correlated. So that disallows assumption 3. So it means that the W and the potential outcome YT, given the filtration, are correlated. Okay, so that's not allowed. But if I was to make these innovations here uncorrelated, then it is a potential outcome time series. So it just gives you an illustration that not all time series are potential outcome time series. You have to have particular structure. If you have that particular structure, then you can go to the races. Then you're in a chance to make some causal statements. Okay, and then this is the more interesting case. So this is forward-looking expectations. So lots of macro models, of finance models, have this type of structure. Suppose the treatment is given by maximizing expected utility, where utility depends upon outcomes and the treatment. So here's the outcome. The W is what the treatment has been up to time t-1. Now we're thinking about a treatment path into the future. So that will affect the outcome path. And then this will be what the treatment path. And then we take the expectation of this thing. So it's the expectation, not the random variables itself. We're allowed to take the expectation of all of this stuff. The expectation is then maximized over the future treatment path, and you choose the W which maximizes that stuff. So U star here is the utility function of future outcomes and treatments, and this decision rule delivers WT and thus YT with the treatment path, and that's a potential outcome. That's a potential outcome time series. So that structure is a potential outcome time series. And you don't need rational calculations. There are various discussions in the paper about, you can extend this in different ways. So that's kind of interesting. Okay, so.
Neil, can I interrupt? We're about halfway. We've got a few people with questions. Yeah. Is this a good time to take questions?
Yeah, sure. Yeah, I'm about halfway too.
Okay, that works out nicely then. Okay. Well, let me unmute a couple of people. The first one, I'm going to call on Kevin Shephard to ask a question.
Hey, that's nice.
Okay. Kevin, if you're there, you can go ahead and ask.
Yeah, I need to unmute myself as well. Just wondering, when I saw your slide, when you're going through your details, does the time series Y, is it important that it's observable at time T to sort of do this? Because obviously you think like macro variables and a lot of things, we don't kind of ever really know where they are, or is that just a sort of precision issue, as you would call it, rather than an identification problem?
So I'll talk about an issue to do with that later, where I will assume that the treatment is not necessarily observable, but I'll estimate the treatment. But we haven't talked about in this paper what happens when the outcomes are not observed. Okay, so I haven't thought about that case. Like the case where the treatments are not observed is a famous problem in macro, where you're trying to measure the monetary policy shock, and you don't estimate. You have to estimate it. So we'll deal with that later in a slide. Okay.
Great, thanks, Neil. So we've got another question. This one's from Rob Engel. Rob, I'll unmute you and you can ask your question.
Hey.
Let's see. Rob, are you there? You might have to unmute your microphone.
Okay, did that do it?
That did it?
Yeah.
Okay. The assumption of unanticipated outcomes must eliminate any deterministic treatment processes, including, it seems to me, a constant. And I would think that an awful lot of the cases where we're interested in causality would include constant treatments. Am I correct in that interpretation?
So you're thinking about, well, that's an interesting, that's an interesting thing. Shall we talk about that later? Like, I think that's quite an involved question.
Okay.
It's certainly a very interesting question, which is, Rob's interested in at time one, there's a treatment, or you can be under control, and then that holds for the rest of the data. That's an interesting setup, and you can define, that would just be that W1 has some particular feature, W2 is kind of vacant, right? But let's talk, I think we should talk about that later. I think that's not going to be core to what I do, if that's okay with you.
Okay, sure.
Yeah.
Okay, Neil, we've got one last question and then we'll let you go on. So the last question is from Aravind Srinivasan. Aravind, I'll unmute, and if you can ask your question.
So in the example that you were talking about, where the traders are given the opportunity and evaluated against the computer model, wouldn't that be a more randomized control trial rather than a potential outcome?
Yeah, this is the time series version of what you just said. So you're exactly right. I mean, I'm just trying to build a time series analog of the way you think about randomized control trials. That's what we did in the JASA paper. And now what I'm trying to take is the next step, which is to think about, do any of those concepts carry over to when I do observational studies rather than randomized experiments? Is that okay?
Yeah, thank you.
Okay, all right. Thanks for the question.
Okay, thanks, Neil. Back to you to finish this.
Okay, we're in the home straight now. That's the hard lifting. So everything else now is not too bad. So we're going to we have this potential outcome time series. Now I'm going to define what I mean by causality. So causality is I look at the potential outcome given the treatment in the past. I'll have some lag P here. And then I will compare a treatment path W going from T minus P up to T and the outcome that would hold if again, this is what's happened in the past. That's the treatment path in the past. And now I'm going to compare it to changing the treatment in the future. So this is the treatment in the future, or from time T minus P up to T, will move from W to W prime. And then how the outcomes respond to this as I physically move the treatment path is what I mean by causality. So this is the causal effect at time T. Okay, so that's what Bojinov and I did before. And then then the question is, which W's and which W primes do you compare? And here in this paper, Ashesh and I introduced what we call a causal response function, because what we're going to do is, in this paper, what we're trying to do is take our potential outcome time series for randomized experiments and then move it towards things that empirical people in economics see when they think about these types of response functions. So this is our first step in doing that. So I'll write W prime as the potential outcome if I saw a path of the treatment W prime in there from T minus P up to T. And then as usual, I'll call YT the stuff with the W's. And then causal response function is to compare Y to Y prime. And here you'll see something that begins to look familiar. I'll fix the WT minus P at W, and then I'll fix the counterfactual WT minus 1 prime at W prime, and then I'll, there'll be an information set as well in there. So when I do that, I call that a causal response function, where this expectation is generated by the joint distribution of the Y's and the W's, the Y primes and the W primes given the past. Okay, so that's a causal response function, and in a minute I'm going to simplify it. And then that's the thing I'd like you to focus on. So we're on a journey here. So that's a causal quantity because it looks at differences of two different things in here. And then it's simplified because I take this expectation, integrating lots of stuff out. Okay, and then that varies over T, and it varies at different lag lengths. And then the causal estimand is the average of those over time. Okay. If I was to make some assumptions on the behavior of these counterfactuals, I don't really want to get into their details. So they're done basically to deliver something that is attractive. So I'll take this expectation in here. I'll simplify the expression I just got into this quantity, and it's this quantity I'd like you to take home tonight. So this is what we call our causal response function that we're going to use for observational data. So this is the expectation of YT given the treatment path is the treatment at time T minus P is W, and the information set minus the expectation of the same quantity just moving W to W prime. And when W prime is 0, this is the generalized impulse response function of Coop, Pesseran, and Podder. So what we've done is we've taken the generalized impulse response function and we've endowed it with causal meaning. So if you have a generalized impulse response function and you can simultaneously tick off the potential outcome conditions, then your generalized impulse response function has a causal meaning. Okay, so that's basically our major, in a way, that's our major result in this paper. The causal response function is our favorite summary measure for practical causal studies of observational time series. It's the basic measure that we think is important. Okay. And what we do is we estimate this quantity or the average of it over time, and then we show that you can get a non-parametric consistent kernel estimator of this quantity just using the potential outcome structure, a very little bit of regularity. So this means that the average dynamic causal effects can be non-parametrically identified solely by assuming a potential outcome time series. This means that identifying causal effects by what are called shocks, as econometricians often do through Frisch-Slutsky paradigm, actually misses the point. They're not identified by shocks. There are no shocks. We haven't introduced what a shock is here. They're identified because of the potential outcome structure. And later we're going to define a shock, and what the role of the shock will be, it'll help us with statistical precision. It helps us estimate things more precisely. It doesn't help with identification. Okay, so that's one of our results in our paper. So this is the next step, which is the special case of this structure is impulse response function. So if the world is strictly stationary, then you get a famous impulse response function of the expectation of Y given the treatment at time T minus 1 is W minus the same thing at W prime. You know, that was made famous by Sims. As it stands up here, if you just have this term, that has no causal meaning, right? This is just the difference of two expectations. It has no causality in it. Sims gave it causality by using a vector moving average, a vector autoregression. That's what imbued it with causality. Now we imbue it in a different way. So we assume Y and W are stationary potential outcome time series. Then if the expectation exists, the expectation, the causal response function, is the impulse response function, where the expectation is generated by a stationary distribution of treatment and outcomes. And again, if you want to estimate that, you get a t to the 2/5 rate. So that's a non-parametric causal meaning to impulse response functions. So if you want to do an impulse response function, you know how to calculate this. It's a famous thing, non-parametrically. And now if you can additionally satisfy the potential outcome stuff, then you can go from it just not being a summary measure, but a causal measure. So that's the point of it. Okay. So that's mostly what this paper does. And then there are a few other things. So the paper defines what for the first time, a linear potential outcome time series is. A linear potential outcome time series is when the W's move the Y's move with the treatments in a linear way. Okay, so it doesn't mean that the Y's and the W's are a linear process. It means that the Y's respond to the W's in a linear way. Okay, if that's the case, we call that a linear potential outcome. And then we also introduce for the first time what we mean by a shock in a potential outcome time series. So a shock is a treatment which is a martingale difference sequence. Okay, so if the shock is specialized to the case where you have the treatment is a martingale difference, then we call that a shock potential outcome time series. Okay. So if you have a linear potential outcome time series, which is this guy, so then the causal effect of moving from W to W prime is just the differences of these multiplied by the betas in here. Then under linearity and shocks, the potential outcome time series, sorry, the causal response function is the difference of the betas in these coefficients averaged over time. So they're time averaged of these betas in here. Okay, so that's what the causal response function gives you. Okay, and so if you have a linear shocked potential outcome time series and you regress the Y's on the lag W's, this is called a local projection estimator, then what it actually estimates is a weighted version of these betas in here, not the average, but the weighted betas determined by the expectation of these W's. Those are the weights in here. And typically that's t to the half consistent. So if you add linearity and shocks, then you get a faster rate of convergence. So that gives you more precision. So it makes linearity and shocks more precise. And under stationarity, linearity and shocks, then beta hat will converge to the long run average of this quantity. So this is what economists think they're estimating. And it is what they're estimating if their system is stationary, linear, shocked, and potential outcome time series. Okay, if it isn't, then you get this mix, this weight in here. Okay. Then there's an instrumental variable version of this. This will be my kind of last theme, and then I'll stop. So there's a potential, there's an instrumental variable version of this. This is connected to Kevin's question. So let's start with the example. So Y is a macro aggregate like unemployment. WT is a monetary policy shock, but we can't see it. So what we do is we estimate the monetary policy shock, maybe using high frequency financial data. But those things are different than one another. So there's a focus in the literature on what's called local projection instrumental variables regarding this guy as an instrument rather than the actual WT. Okay, so there's a nice literature about that. In our context, we have a formalization of that in a model-free way, okay, which is YT and VT is a potential outcome time series where VT is the WT and some other variable ZT, which satisfies an exclusion restriction where the Zs don't impact the outcomes, and where the Zs are not independent of the treatments. If that's the case, we call this system an instrumented potential outcome time series, and the Z's are an instrument path. Okay, so that gives you a non-parametric definition of what an instrument means in a time series context. Okay, and then we kind of show that you can estimate it, etc. So I think I'll stop there, if that's okay with Andrew. So these are my conclusions. So what we do is we have a formal model-free definition of causality in time series, potential outcomes, and these TOR things. Our favorite form for practical measures in observational time series is this thing, causal response functions, the difference of two expectations, changing where your treatment is at time t minus p in here. And we can non-parametrically estimate this, and it gives a causal non-parametric causal meaning to the generalized impulse response functions. And then stationarity plus POTS, potential outcome time series, implies that delivers the impulse response function. And that gives non-parametric causal meaning to an impulse response function, but it still gives you a slow rate convergence. Linearity plus potential outcomes means that you can estimate this at t to the half. Did you hear that?
Yes.
There was thunder. It's like either people approve or disapprove of this talk. Who knows what's going on? Anyway, okay, so there you go. So that's linearity plus, and then linearity and shocks, potential outcomes, allows you to understand local projections. And then with instruments, you can do local projection, instrumental variables. So I think that's enough for me. Is that okay, Andrew?
Perfect. That's just right on time, Neil. Thanks very much.
Okay.
Okay. Well, now Jean-Pierre Florens is our discussant, and I'm going to be the person running the slides for him. So let me share my screen with your slides, Jean-Pierre.
Okay, thank you.
So can you see these slides?
Yes,
okay, will you just tell me
fine.
when you put the page down, and I'll do so.
Okay, so thank you very much for giving me the opportunity to speak at the SoFiE Seminar. It's the first time for me, and to discuss this interesting paper. So can you move to the next slide, please? Okay, so this paper is interesting in particular because it provides a connection between two important fields in econometrics, the treatment model and the time series. And the treatment models has been developed essentially in microeconometrics, in return of schooling, in education, in different topics of microeconometrics, and time series in a different field. It is interesting to link the two approaches. I think this is interesting for different reasons. And the first one is that some variables in macroeconomics models should be naturally considered as treatment. And I have in particular in mind the political economic decisions, which may be sometimes considered as exogenous or endogenous variable, but I think that the right status of this variable is to consider it as treatment. I have more questions about the relation between treatment and shocks, because for me, treatment is a decision, and shock is something which is purely random and not decided by anybody in the economic system. But this is for me a little surprise to see the relation between treatment and shocks, but it is a theory, and I can accept that definition here. So the main interest of treatment model is to provide a good framework for a discussion of the analysis of causality. And this is an old story in econometrics. So for at least 40 years ago, there was a big debate about different concepts of non-causality, in particular concept by Ranchard, Sims, and for example, the Zellner approach at this time. So could you move, please, my next slide? So I briefly recall the different elements of the debate between different concepts of causality. So there is the first approach, which has been recalled by Neil, which is causality in terms of conditioning or conditional independence. So take two random elements, Y and W. I have no process at this stage. And I say that W does not cause Y if the two variables or two random elements are independent. So this means that the conditional mean of any function of y given W is equal to the marginal expectation of that function. So this is a purely symmetric concept, but if you introduce time and stochastic processes, we can create asymmetric concept. For example, the standard definition by Granger is that the future of the y given the past of the y and of the W only depend on the past of the y, and in that case, we can say that W does not cause y. As they said, it is not really a concept of causality, it's a concept of prediction. So the treatment models give a good framework to define causality. So I recall the framework of the treatment that has been done, but in a more general way, that time series. So if W is a treatment, it's a non-random element, it's an index. And the counterfactual model is a stochastic process where Y is indexed by the treatment. So it's like time, but we can imagine that for any value of the treatment, there is a distribution of the outcome Y. And so in that case, W does not cause Y if the distribution, the marginal distribution of Y for the value of the treatment W is the same as the distribution of Y given the value, the outcome is the same for the value of the treatment W prime here. So in that paper, there is an extension of the discussion between different concepts of causality, but introduces the dynamics model. So can you show me the next slide? So the basic model of the paper is the following. It may be considered, it divided in three parts as usual treatment models. There is a counterfactual model, the assignment part, and the observations. The counterfactual model is like the previous case, except that W and Y are stochastic, are processes. So Y is a sequence of treatment. At this stage, it's not random, it's a sequence of treatment. For each sequence of the treatment, you have a stochastic process. The outcome is itself a stochastic process with this assumption that YT only depends on the past of the treatment, but this is intuitive, but we can fix model without this assumption here. So this is the first part, the counterfactual level. There is a second part where this is assignment process, or somebody, some authority or something, assigns the treatment randomly, and there is a realization of the treatment. And the data, for the data, we observe the assigned treatment and the value of the outcome for this particular assigned treatment. So this is the usual model. This is a nice extension of what it has been done in microeconometrics and by many people like Lechner in particular for dynamic treatments and many people here. So could you move, please? So treatment model asks a lot of questions, in particular for identification, because it is like a stochastic process where you just observe one value of the stochastic process at a stopping time. So it's difficult to infer the distribution of the stochastic process, observing only one single observation at a time which is random. So here, this is the same, but the treatment plays the role of the time in the stochastic process. And so the more standard assumption is to assume randomization. So at the more general level, randomization means that the assigned treatment is independent of the sequence of the counterfactual processes. So this is very strong hypothesis. And under this very strong hypothesis, the distinction between fixing and conditioning disappear, because actually the value of the outcome at the particular value of the treatment may be observed or estimated as a conditional distribution of the observation given this particular value of the treatment. So under that case, I think the main interest of the treatment model partially disappear because the two concepts of fixing and conditioning reduce to the same thing. So in the time series model, like it has been done, what is proposed by Nile is to give a definition of randomization or unconfirmedness conditional, because this first definition of randomization has been extended by many people to conditional randomization, or to the fact that there is a selection only on observable variable. So in that case, this definition of unconformness is extended to a dynamic version of unconformness, which is formalized by the conditional independence I have written here. So the history of the treatment between 1 and t is independent to the conditional, to the counterfactual process, given the past of the treatment and the past of the observed outcome. And in that case, I will not repeat the three equalities I have. So the fixing the value of the treatment at some level or conditioning given the past at this level remains the same thing. And this is not sufficient to treat all the variables. I give all the case. I give an example here. There was a big debate about the efficiency of the treatment in the recent COVID pandemic. And so criticism between people who would defend some treatment is that the treatment is not assigned randomly. And so we cannot infer from the result of the treatment any conclusion about their efficiency because the hypothesis of randomization is not true. But econometricians know that it is possible to correct the absence of randomization by using different techniques and to correct the observation on unobservable. So could you move, please, next?
And just Jean-Pierre, there's 2 minutes.
Okay, so there is different approaches to non-randomized experiments. In econometrics, it is usual to use instrumental variable or control function or to introduce another to complete the model. But there is other strategy to treat non-randomized model like G-computation, for example. And so I want to say few words about IV or instrumental variable. The two main assumptions are the fact that the outcome does not depend on the IV, but the treatment depends strongly on the IV. And this is the point which I have not seen in the paper, what kind of dependence between the IV and the proxy you need to estimate, to identify. In particular, in linear model, we should have a rank condition. In a non-linear model, we have something like a completeness assumption here. And I want to say also that the concept of proxy, which is very similar to two-stage least square in the standard econometry, is not so easy to generalize in non-linear model. And I want to conclude by two ways to extend the concept of IV in non-linear model. So can you go through the next? So this is the standard case. I take the counterfactual model in a non-linear case. So the treatment depends on the history of the treatment, of the history of the outcome, of the noise. And we have the observation and the filtration of instrumental variable. So the standard assumption from IV in a microeconometrics model is to say that the conditional expectation of the residual given the instrument, okay, in the filtration of instrument, is equal to 0. And then this leads to estimate the function phi at the solution of an integral equation. This is not sufficient to treat all the case. This is an interesting structure because this is related to what I have called Meyer IV decomposition of a stochastic process. You may decompose a stochastic process into two parts, into some part which is predictable with respect to some filtration, and the part which is a martingale with respect to another filtration, instead of having the same filtration for the two parts here. But we can extend that, and I will to see that at the end. We can apply a differential operator on this equation here. So could you move to my last slide, please? Okay, so you can, if you have a differential operator, take, for example, the derivative with respect to some instrument here. And if you assume that the expectation of the derivative of the noise is equal to 0, given the filtration of the instrument, you get this type of equation, which is here. And in some case, I have not given the theory of that, but in some case, we can commute the derivative with respect to the instrument with the derivative of the treatment, of the observed treatment. There is a control function assumption under that, multiplied by some terms, and then you get something like the equation I have written down this slide. So the ratio of the two derivatives of the y given the instrument and of the instrument given the treatment given the y is equal to the expectation of the derivative of the w. So this is something which has been studied in microeconometrics. This is related to what is called the MTE, or to the late. This is a continuous extension of the late. And I think this should be extended to dynamic model. And I want to finish my last sentence. There is a literature on weak instruments. So is it possible to do this extension to the framework you have presented here, which is a way to see a weak relation between the instrument and the treatment. Okay, so thank you very much. I think I should complete now.
Okay. Thank you very much, Jean-Pierre. Well, we're running a little bit late, but that discussion was so good, I thought it was worth having a few extra minutes for it. So Neil, if you would like to respond for a couple of minutes, and then we'll open up for questions from the audience.
I think the last two slides gives me quite a lot of homework to do. So I just want to thank Jean-Pierre for being as inspiring as he ever is. Like, it's very insightful, and I think he's just suggested quite a lot of new papers to write. So thank you for doing that. I really appreciate all the work you put into doing it. I don't have any answers he basically asked questions. I don't have, they're research questions. I don't have answers off the top of my head. So I just want to say thank you.
Okay, great. Well, we have one question right now from the audience, and if anyone else, maybe we have two. So the first one.
I think I know the answer to Rob's question now.
Okay.
Because
well,
if he wants to come back, so.
Rob, you're open to ask a question again if you like.
I was going to ask a different question.
Go for it.
Am I okay?
Yeah.
Okay. I guess I'm wondering what Clive would say about your talk. And I think my guess, here's a guess as to what the answer would be. That you've given a set of assumptions under which his non-predictability result would imply causality.
That's not quite right.
Okay.
So let me, I appreciate, so I think you're talking about really this is, I think the Granger causality stuff is mostly about assumption 3. It says the treatment at time t given past is independent of all the potential outcomes in the future. Okay, so what does that say? It says that the treatment doesn't Granger cause all the potential outcomes in the future. It doesn't say anything about the outcomes that we actually see. It's just that the potential outcomes are not Granger caused by the treatment at time t given the past. So I think Clive didn't usually think about kind of latent variables, right? But if he did, that he's appearing in here. Is that what you're talking about? Maybe I didn't understand.
Well, I thought that the impulse response function
okay.
was sort of the regression of future values on past values. And,
yes. Yeah, that's true. So so it's true that if the process is strictly stationary, then we have this measure that's up here, and if that was 0, we would have using this measure, W is not Granger not causing YT. That's right. As long as we also have a potential outcome time series. So we're close to that. Now we're getting close to Clive. So I can see that now. Thank you. And but we have to have this auxiliary assumption, right? We have to have this auxiliary potential outcome thing that's sitting in the background, right? So in some sense, that's outside Clive. But
suppose you gave him all your assumptions.
Yeah. if I was to have my assumptions and then I was to do Granger causality test,
Right.
then and that's then saying there's no Granger causality, then that is causality. That's right. So that's what you're saying. Is that yeah, okay? Thank you. That's great. As ever, you get to the core of issues. So that may well help a lot of people. It helps me. So thank you. Does that make you more interested in this stuff now?
We'll let Rob off for answering that. We've got one last question. Herman van Dyke, I'll unmute you and you can ask your question.
It's like all my friends. It's such a pleasure, this seminar.
So, hi, Neil.
Hi.
All right. So my question, very simple one. So it's about the characterization of potential outcome series. How you characterize it very often as stationary and regular. And like in forecasting, where I have this enormous distinction between unit roots, non-predictability, or have the best forecast for tomorrow, value of today. How is it when, in your case, your potential outcome series have become near that borderline? It's in a sense a bit similar to Jean-Pierre's question about weak instruments. And what's going on? So if we are even pragmatic, in reality, there are some of our leaders who have a treatment in macroeconomics where the potential outcome series could be disastrous. And so you've given very precise restrictions so that you have linear stationarity. But what would you say about the danger of getting to borderline cases? Thank you.
Oh, gosh. Herman always asks questions which are quasi-philosophical, which makes me feel inadequate answering these questions. So it's like, so I would guess I would answer that, like sometimes non-stationarity is a blessing, right? Which is it allows you to learn about the economy much faster than you would if the world was just stationary. So it just makes things technically harder. So there are some advantages. And then Jean-Pierre was quite correctly saying that, you know, when we have instruments, then sometimes, often, usually things become, you know, weak and inference is often difficult. And so he was reminding us of that. And so there are two extreme cases, right? I guess my student wanted to like really relate to what the macroeconomists do, and so that's like why we're kind of using the stuff at the end of the talk. I think from a financial econometrics viewpoint, the most important thing is to understand when you can, you know, because financial econometricians use impulse response functions and generalized impulse response functions. And so using that, understanding when they could be causal and when they can't be causal is kind of interesting, I think. But yeah, you ask a lot of good questions. I don't know the answer. As usual, when you ask questions, I don't know the answer to them.
Oh, it's certainly interesting talk. Thank you.
Thank you. Thanks.
Okay, I think that's a good place to wrap it up. So Neil, if you wouldn't mind unsharing your screen.
Oh yeah, sorry.
That's okay. Well, let me thank you everyone for joining us today. Thank you to the speaker, Neil Shephard, and Discussant, Jean-Pierre Florens. And let me invite you to join us for the next installment of the SoFiE Seminar Series. This will be Robert Engel presenting in 2 weeks' time on a paper on volatility and geopolitical risk. And later this week, there'll be a few more updates of future seminars and panels on the SoFiE Seminar Series website. So please check that out for more information. Thank you again for joining us.